Good morning. So, last class we talked about hypothesis testing, especially large samples and followed by small sample and the jargons, the p value, etc. We solved a few problems and towards the end we looked at proportions, okay. And we know that there are two kinds of errors which we will make, okay. One, we talk about what is type 1 error, which is fixed by fixing alpha. So, alpha is the type 1 error where you are rejecting the null hypothesis even though it is true, right. So, that will be typically low, you do not want to change the status quo with less evidence, right. So, you usually have alpha to be very small so that the type 1 error is small. The other error which we make is beta, which is the type 2 error, the probability of accepting null hypothesis even if it is false, right. Even if it is false, what is the probability that I will accept the null hypothesis? That cannot be 1 minus alpha, then you do not have the diagonals at all. So, that is where we are going to talk about, we are going to calculate type 2 probability, error probabilities or more about beta, we are going to learn more about beta, okay. So, I will tell you the, okay, let us move on to the concept before even doing the example. Okay. So, let us see how to find out the probability of type 2 error beta. Okay. So, you have your null hypothesis, your alternate hypothesis, mu equals to mu naught equals to mu naught, okay. And what do? You actually suppose that the null hypothesis is false. What are we saying? The null hypothesis is false and the true value of the mean is mu equals to mu naught plus delta, okay. So, what is my truth? So, remember I have to assume about truth, okay. This is my assumption. To calculate type 2 error you need to know assumption about truth. Okay. So, the null hypothesis is false and you are assuming that the truth is mu equals to mu naught plus delta, right. And of course, we know how to calculate the z statistic. Z is what? X bar minus mu naught by sigma over root n. In this case, if I add and subtract delta, I am going to add and subtract delta. So, I can write like this, okay. All I did to the z statistic is nothing, I have not changed it, I have added and subtract and grouped things together, okay. So, now the true therefore the distribution of when H1 is true is what? The distribution of Z0 when H1 is true is what? H1 alternate is true. So, remember when null is true, what is the distribution? Z0 is approximately normal what? Mu naught comma. So, if I remove this is going to be 0 comma 1, it is standard normal, right. If H0 is true, this is going to be standard normal, but if H0 is not true, then what is the distribution? The distribution becomes, your assumption was the center value was mu naught. So, Z minus mu naught should have given you 0 if the null hypothesis is true, but the null hypothesis is not true. So, then what do I have? What is the extra term that is going to come in? Is going to be delta root n by sigma, right. So, you understand how did I get this? I am adding and subtracting delta, I have clubbed things together, okay. Make sense everybody? So, what is the distribution? Z0 is normal delta root n by sigma comma 1, instead of 0 comma 1 it has become delta root n by sigma or delta by sigma over root n, that is what I have rewritten as delta sigma root n by delta square root of n by sigma, okay. You understand this term, right, this step. So, we have just simply added and subtracted mu naught plus delta, okay, plus delta by, which is nothing but delta square root of n by sigma, okay. So, if null is not true, then Z is, this term goes away, and of course I have divided by standard deviation, so this is going to be, the standard deviation is going to be 1. Okay. So this is my distribution of Z naught if H1 is true, and if H naught is true, it is going to be 0 comma 1. So these are the two distributions you are going to talk about. Okay. So we have two distributions under H naught, mu equals to mu naught, which is normal 0 comma 1, because you have standardized it. This the test statistic is z x bar z equals to x bar minus mu naught by sigma over root n. That is what you compute as test statistic. That if it is true, it will be the true distribution is normal 0 comma 1. Now if that is not true, then what is the distribution? It is going to be delta by sigma over root n comma 1. The delta is the difference between the what? Underlying is mu naught and the true mu. So mu equals to mu naught plus delta, that is what we have assumed. Delta could be positive, negative, it does not matter. Delta could be on the right, this could be on the right hand side or on the left hand side. If delta is positive, this curve is true. If delta is negative, I will have it in the left half, right. So mu will be equals to mu naught minus delta, then this will be my center and the curve will be on the left hand side. Clear? Is it making sense, everybody? This is very important, this is the conceptual understanding. Okay. So I have two standard normal distribution, two normal distributions. One is standard normal 0 comma 1, the other is 1, but it is not standard normal because mu is not equal to mu naught and the difference is delta by square root of delta by sigma over root n. That is what the second one is. Clear? Now tell me how will, what is beta? So what is Z alpha by 2 to minus Z alpha by 2? This is my acceptance region, right. This is where I will accept null hypothesis. Accept H naught or do not reject H naught. Clear? That is my acceptance region. So the overlap of the second distribution with the first distribution in the acceptance region is what beta is. The overlap of the mu naught distribution and mu naught plus delta distribution, the overlap in the acceptance region is what the problem is. See this region I am going to accept, see this region if you look at overlap, what am I going to do? I am going to accept H naught even though it is false. Actually it has belonged to what? It has belonged to the tail of the second distribution, but that has overlapped with the acceptance region of the H naught and therefore you accept H naught even though if it is false. This overlap region is the beta. Beta can happen only in one side. Now you understand, beta cannot happen in both sides. This distribution cannot overlap in the right side as well as in the left side. Okay. So if we have the other curve could be like this. This is my beta in the left hand side, right. So the other curve could be on the left hand side, but beta will happen only in the right side or in the left side depending upon the truth, right. If the truth is on the positive side, then beta will be that's in the right hand side, truth is greater than mu naught, and truth is less than mu naught, it will be on the left side because you have two distributions. Clear? Make sense everybody? So this is what beta is. So from examining we can see if note that if true, if H1 is true, a type 1 error is made only if Z naught, where Z naught belongs to this thing, that is the probability Z naught falls between minus Z by alpha by 2 and plus Z alpha by 2 given that H1 is true. So what is beta, probability of beta? Probability of beta is nothing but probability that Z naught lies between minus Z alpha by 2 and plus Z alpha by 2 even if H1 is true and H naught is false. Okay. Now tell me when will the overlap be more? So you look at this, right, this is simply overlapping of two distributions, right. The overlap in the acceptance region is what is beta, clear. Now when will the overlap be more and when will the overlap be less? When delta is small, what will happen? More overlap. So that means if you want to distinguish finer things, then obviously what will happen? The overlap will be more, type 2 error will be higher. Even if you fix type 1 error, type 2 error, so there is no point playing around with both type 1 error and type 2 error, okay. We know that they are inversely proportional. So if you fix type 1 error, type 2 error will depend upon delta. The more finer you want to resolve, the more overlap it will be and there will be more beta, understand, right. So that is what it is. So the finer resolution in distinguishing between null and alternate hypothesis will result in more and more beta. How do you reduce beta? How do you now reduce beta? By increasing only n. Look at this, delta square root of n by sigma. So now if I want the second distribution to be pushed aside, what should I do? Increase n, but even if you increase n, it scales only square root, not squared, square root. So if you do 1000, you are pushing it by 10 times, and even if you take delta as 0.1, 0.1 into 10 is what? 1, and it is also divided by sigma. So 1 over sigma. So 0 comma 1 and 1 over sigma comma 1, even if you do 1000 samples, and delta is 0.1. Delta 0.1 is very tricky, you understand, it is 1 over sigma. 1 over sigma, your sigma is like 1, that itself is 1 comma 1, okay, there will be a overlap. If your sigma is even higher like 10, you are again back to square 1, there will be a heavy overlap, right. So that is where n becomes critical, and the distributions can be separated apart only based on square root of n, not square of n or not even n, it scales square root of n. We will do hypothesis for standard deviation, that is actually the most important, even compared to mean. Which one? No, I am not worried of, I am testing for mean, I do not care about standard deviation. I have normalized it so that my standard deviation has become 1. So here you are saying the separability is in terms of mean, the truth and the alternate, the separability is in terms of mean, but that is a feature. If you look at it in a machine learning terms, that is a feature I am looking at, mean as a feature to distinguish two categories. I can always do variance also, which we will do in the course, okay. Here mean is what I am looking at. Make sense everybody what we are trying to do? So the lesser the delta, the more the overlap, the more the beta, okay. The only way to do it is resolve using higher value of n, okay. So beta, if you want to technically look at it, this is the idea behind beta, the shaded portion, this is nothing but the phi stands for the CDF of normal distribution, phi of z alpha by 2 minus delta sigma over root n. So what is this region up to here? This minus this, okay, phi of z alpha by 2 minus delta root n by sigma minus phi of minus z alpha by 2 minus delta sigma over by delta square root of n by sigma. This is my beta itself, Okay. So, I am calculating the overlap region. Okay. One is this one Z alpha by 2 minus this one, and the other one is minus Z alpha by 2 minus this one. Okay. The second, only one term will be present, not both the terms will be present. One term will invariably go to 0, because you either do it on the overlap on the right hand side or left hand side. It cannot, both the overlaps cannot happen. That means your distribution is horrible. In fact, it will never happen. So, one of them will go to 0, depending upon whether delta is on the right hand side or the delta is positive or delta is negative, you will have either one of them. Clear? So, that is what I have said, if delta is greater than 0, you have only one term. Okay. If delta is less than 0, then you will have the other term. Okay. From this you can determine a value of n that is required to fix the beta. So, for a fixed alpha, okay, for a fixed alpha, what is the value of n I should choose to get a desired beta? Remember, the sample size selection was very important. Where else did we do the sample size selection? Where did we do sample size selection? To reduce the error, the standard error, right. If I fix the error and I want, if I fix the range and if I say I want to be 95% sure, what is my n value? That is for confidence intervals. Here what am I saying? I am saying let me fix alpha, okay. I know some value of sigma, the standard deviation, I assume some value of sigma. So, for a given alpha, okay, and for a given confidence interval, the given confidence requirement like 95% or 99%, what is the value of n to make sure that you achieve desired beta? So, let us say I want only beta to be 20%, that means 20% of the times I will make an error, that is I will accept null hypothesis even though if it is false. At least 80% I will be rejecting null hypothesis if it is false. Okay. 80% of the time I will be right, 20% of the time I may be wrong. Okay. If I want beta to be 0.2, then what is the value of n? How do I derive it? That is what from the beta formula, if you rearrange, you should be able to do it. Okay. So, this is the n value, z beta is the formula I have taken here, this is z beta. Okay. So, I have n value here, right. So, you can derive an n for a given alpha, assumed sigma and an assumed delta. So, remember delta has to be assumed. So, if you want to calculate beta, you should know about the truth, okay. You cannot calculate beta without knowing the truth, right. So, you assume a truth and let us say I want to resolve that much accuracy between mu naught and mu alternate, okay, and I say I want to resolve within 1 or even 0.1 value, okay, 0.1 amplitude, then you calculate what is the n value required to do that, okay, for a desired beta. So, these are many things at play, okay. So, your alpha, your beta, the delta and the n values, all 4 are at play, okay. Make sense everybody? So, how do we start? So, as I said, to calculate type 2 or beta, probability of type 2 error, that is also called beta, calculate the value of x bar that divide the do not reject region from the reject region. That is typically we know that we are only doing a reject and not reject, 2 tail test, 1 tail test, upper tail, lower tail, we know that is step 1, okay. Calculate the z value of x naught assuming the alternate hypothesis mean is the true mean, okay. So, now you are saying alternate hypothesis is the truth. So, you calculate the z, okay. The probability of getting this z value for this acceptance region is beta. You understand the statement? I do not know whether you can get this. The probability of getting this z value for the acceptance region is beta. Remember, you have assumed alternate to be correct and you have did a alternate z. Typically you do mu naught, here I am saying you do with mu alternate. What is the probability of getting this z value within the what acceptance region? That is nothing but your beta, simple. So what is the accept beta for a particular alternate hypothesis? You can get this answer simply substitute instead your regular test statistic is what, z equals to x bar minus mu naught by sigma over root n, and then you reject or accept the null. What I am saying to compute beta is z equal to x bar minus mu a by sigma over root n, and you look at what is the probability of this z value lying within the acceptance region, simple. Okay. So let us take this example, okay, we will do a problem so that you understand. Let us take a simple example, mu equals to 60,000 for that whatever the postdoc salaries, and then mu naught equals to 60,000. Okay. You can calculate the test statistic, z equals to 0.613 and z alpha by 2 is 1. We did not reject this hypothesis earlier, okay, we did not reject this hypothesis earlier, we know this problem, but what if the true mean is 62,000. So what am I saying, the true mean is 62,000 or the delta is 2000, okay. So what is the beta? Upper and lower limits we know, right. So we know the what I call the acceptance regions, right, upper quartile, upper OU, OL, ZL is known to you, Z upper is known to you, this is the acceptance region, minus 2.8 to 1.045 is the acceptance region, clear. So now what do I do, beta lies between, what is the region, this thing, beta is between minus 0.2 to 1.045, that is the overall region in which the overlap happens. Now beta is nothing but the probability of z lying between minus 0.28 to 1.05 is 0.8511, that is the overlap, possible overlap. Here overlap is very high, here overlap is very high, why? Because delta is only 2000 and look at the standard deviation, the standard deviation itself is 2100, so there is a very heavy overlap, okay. So in this case beta will be very large, you cannot distinguish 60,000 and 62,000, that is what I am saying. Why? What is the reason here for not distinguishing? Your error is what, 0.85, 85% of the time you will accept null hypothesis even if it is false. Why is that? Why is that in this case? Why is there a overlap? See, original is $60,000, your alternate is $62,000. The key is not the $2,000 become a number, sigma. The sigma value itself is 2100. So you are not your mu alternate is not even 1 sigma beyond. So you will obviously make a big beta because there will be obviously a big overlap, that is what it is, clear, right. So this case what did we do, remember this is my ZL, ZL is nothing but, so I first calculated what, calculate the acceptance or rejection ratios, right. This is upper tail x bar mu naught plus r, this is the lower tail, the two tailed, I have this confidence limits, these are my confidence limits, right, upper and lower, x naught lower, x naught upper. So I have calculated this x naught lower and x naught upper, okay. So this is my x naught lower, x naught upper. Then what is ZL? What is the next step? Assuming Z equal alternate hypothesis is true, calculate the Z values. So what did I do? I calculated Z lower, Z upper, because it is a two tail test, I will have Z lower and Z upper, okay. So now what is the overlap region? The overlap region is nothing but the probability of Z value lying between these two, okay. So that is nothing but 0.85. Does it make sense? And in this case if you take lower, this will be 0, this will be 0. You go and look at it, probability that let us take this table once again. Why will this probability of ZL will be 0? Because this is on the left hand side and you will have only on the right hand side, because it is 60,000 and your truth is 62,000. So look at this ZL, probability of Z lying between. So if you take the tables, okay, see minus 2.85 is equivalent to plus 2.85, right. So plus 2.85, what is the region? 0.0022, that means the overlap is literally 0, okay. Whereas what is the maximum which contributes to the maximum? The right hand side. The right hand side value is what? 1.045. 1.045, if you come and look at 1.1 is there, 1.045, that is like 0.1, this is what. So this is what I think so this is what makes a difference, 1.045, if you look at it will be a bigger value, okay. So that is what is contributing, only the right side will have the value, the left side will not have any value at all. Does it make sense everybody? Okay. Okay, if you compute this value, you will know you should get it to be 0.85, okay. So that means in this case the power of the beta value is high and we define what is known as called as power of a test. This is a very important term in statistics, especially when you are doing hypothesis testing. The first question they will ask is, what is the power of a test? What is the power of a test? If the null hypothesis is wrong, you should reject it. If the null hypothesis is wrong, you should be able to reject it. You want the power of a test to be very high, okay. So that is what power of a test is given by 1 minus beta. 1 minus alpha into percentage is the confidence intervals, confidence percentile. 1 minus beta is nothing but your power of the test. 1 minus beta percentage is nothing but your power of test. 1 minus alpha percentage is your confidence. So that is what type 1 and type 2 error is significant, okay. Significance of type 1 and type 2 error. So the power of a test is simply determined by 1 minus beta, okay. So this is nothing but rejecting null hypothesis if it is false, that is what power of a test is. So power of a test should be at least 80%. A good statistical test should give you at least a power of 80 to 85%, okay, for whatever alpha, okay. So in this case it is a very bad hypothesis test because your beta is very high and your power of a beta is only 15%, power of the test is only 15% in this case. So for a fixed n and alpha, the value of beta decreases and the power increases as the distance between mu naught and mu a increases. This is known for a fixed n and alpha, okay. If the distance between mu naught and mu a increases, beta decreases. For a fixed n, mu naught and mu a, the value of beta increases and the power decreases as the value of alpha is decreased. So this tells you beta increases as alpha decreases. This tells you beta increases, beta increases, alpha decreases. Beta decreases, mu naught minus mu a increases, keeping others are constant. Or for a fixed alpha, mu naught and mu a, the value of beta decreases as n is increased. Thus last statement is what we can use. The others, if you touch, you are touching either type 1 error or you are not able to resolve fine. If you want first two to be constant, the only way to bring down beta is increasing the value of n. Clear? So far so good? The confidence interval is, I will not say null hypothesis because I am also saying how much I can reject the null hypothesis using confidence interval, okay. So that way I will not put it. Power of a test simply says how much am I able to reject the null hypothesis if it is false, that is power of a test, okay. Confidence limit says how much confident am I about rejecting the null. So power of a test simply says how much can I reject the null hypothesis if it is false, how much percentage of the time I will reject null hypothesis if it is false, okay. And this alpha or the confidence limit says how confident I can about this rejection. Clear? Shall we move on? So this is my calculating the beta values.